Okay, good afternoon, everyone. Welcome to the USGCRP Observations Interagency Working Group, or OBS-IWG, seminar series for 2024. My name is Diane Stanitsky. I am from NOAA's Pacific Marine Environmental Lab, and I serve as co-chair of the OBS-IWG along with Barry Leffer from NASA. And today's seminar fits within a series entitled Becoming a Climate Ready Nation, a focus on greenhouse gases. Many of the seminars in this series will be co-sponsored by the USGCRP's Carbon Cycle Interagency Working Group, or the CCIWG, and we absolutely appreciate their partnership. This series highlights many of today's pressing climate topics related to greenhouse gases that can only be addressed using high-quality Earth observations and completed with the help of strong partners across the globe. The series is intended to highlight the influence of greenhouse gas observations on everything from the atmosphere to the ocean to land and cryosphere, and touching on human health across all of those, all within the context of an integrated system with a goal to complete a global stock take every 5 years. And our last seminar was focused on the global stock take. So I'd now like to introduce Barry Leffer from NASA's Earth Science Division, again, co-chair of the OBS-IWG, and Colm Sweeney, co-chair of the Carbon Cycle Interagency Working Group, also associate director at NOAA's Global Monitoring Laboratory. So Colm and Barry, they coordinated today's seminar and will serve as facilitators. So I'll turn this over to both of you.
Thank you, Diane. Good afternoon. Excited to see all of you. I'm the program scientist at NASA's Earth Science Division for Tropospheric Composition, so I handle air quality and greenhouse gases. Chip Miller is a pioneer and innovator in greenhouse gas measurements from both aircraft and from space. He was one of the leaders of the NASA CARV airborne investigation and member of the OCO2 science team, the above science team. I'm just going to put a link to his CV in the chat. I don't want to waste any more time. Chip, please tell us about satellite observations of greenhouse gases. Oh, you're still muted, Chip.
Sorry, I just want to put this up in the right way. And now I want to look at presenter view. So do you all see?
Now you presenter view.
You see my presenter view. Okay, forget it. Okay, but I want to see the notes. So maybe I'll just try to remember what I wanted to say. All right. So thanks, everyone. I'm really excited to have the opportunity to talk with you today. And this is a potential for a major paradigm shift in the way that we think about and do greenhouse gas observations and provide information. Colm tasked me with speaking about what NASA is doing to become a climate-ready nation from the perspective of CO2 and CH4 satellite observations and modeling. But for the first time that I can recall, there's a political pull from the highest levels of government for this kind of information. And PCAST has just articulated a far more interesting and provocative challenge, which is what is our multi-tiered, multi-decadal strategy for satellite observations to inform greenhouse gas measurement, monitoring, reporting, and verification. So this is going to be pretty rapid fire. This is all designed to instigate conversation, and I'd be glad to answer any details. Let's see. So what we're going to start with is the take-home messages. So, what we've got here is the need for an Apollo program to address greenhouse gas emissions reduction grand challenge. And I've labeled this concept Vanguard, since that emphasizes both leadership and being on the cutting edge of this science and technology. And it's way easier to say than the satellite component of an integrated greenhouse gas measurement, monitoring, and information system. So again, emphasizing that it's on the cutting edge, it can contribute to international efforts, as well as invigorate US leadership in things like the Paris Climate Agreements and the Global Methane Pledge. And if one looks at the priorities, as we'll do a little bit later on, things naturally break down into these 3 time phases, which also have different requirements. And so we'll tie this back to national priorities, trying to address this. All right, just the outline so you all are ready to go. And the challenge here is that the problem space is actually global, and this is what the climate cares about, but the solution space where we can mitigate is local. And the information and data that we provide need to span many orders of magnitude in both space and time. This is a chart that is intended to let you realize that the data that we're talking about here and that Arlyn will talk about is really designed to feed the monster. And in this case, it's an inverse modeling system, which provides us the real information that people want at the end of the day, which is what are the fluxes, the exchanges of carbon between the surface and the atmosphere, and are we measuring those and modeling them correctly? So we're going to try and overwhelm this problem with data and use the advantage that satellites provide of providing really big data, millions and millions of measurements per day, to get at the transformation of this problem from something that's mathematically underdetermined to something that is ideally overdetermined, or at least well-determined in the mathematical sense. OCO blazed the trail, OCO2, OCO1 went in the drink, unfortunately, blazed the trail and showed us how to do this, set the gold standard against which all other space-based CO2 measurements are now being judged with a precision of better than 0.5 parts per million. 10 years on, it's now also being transformed into something that can deliver actionable information, such as national level net annual emissions. This is interesting because it's been shown that it agrees well for places where we have good inventories and transparent information. But for countries like Brazil that have stopped reporting their emissions, we can actually provide objective information against which to compare. Or for countries that might not have the technical capacity to report emissions estimates, we can help with capacity building. It's also helped understand some of the extreme events and resolve previously unresolved spatial, in this case, meridional differences, and has led to fundamental improvements in our understanding of the processes and extreme carbon climate feedbacks. And this is going to be critical for what we talk about in terms of the overall strategy and the grand challenge. In terms of fires, some of the mega fires in Australia, these fires were more than 2 times the annual emissions of Australia in terms of anthropogenic emissions in 2019-20. And last year, the big fires in Canada were more than 4 times their reported annual emissions. And it looks like the Canadian fire season is off to another roaring start. We have OCO3 on the International Space Station on the Japanese module. And it's really good at making these snapshot area maps, which can be up to 100 kilometers by 100 kilometers. They're typically targeting either urban areas, large power plants, and in this case here, a power plant complex in China. And it's actually able to help quantify some of the individual plants. And we've got some, emit plume information superimposed on this. And emit is also on the space station. It was not specifically designed for greenhouse gas plume monitoring, but extensive experience with the Avarice airborne instrument, its precursor, demonstrated that emit would have tremendous potential for near global CH4 and CO2 super emitter detection. An example is given in this Science Advances paper, where we really highlighted Turkmenistan as being just an enormous methane source, and subsequent research has gone back into the archive and found that probably since the early 90s, Turkmenistan has been emitting at tons, hundreds of tons per hour of methane from some of their places. Here are some different examples across different sectors of methane emissions that EMIT has seen already. There are more than 1,200 unique detections so far, and that count increases every day. Here's an example of a fugitive emission, an unexpected emission in the middle of Kansas that EMIT was able to pick up. And this is exactly the kind of emission that we want to rapidly detect and identify to pass on to people for mitigation. All right, the International Constellation, CEOS, has done a great job in collecting and cataloging all of this information. And here's an example of the carbon dioxide. Let's call it an ad hoc constellation. I'd say that this is caveat emptor, buyer beware, because not all of these sensors that are listed here were specifically designed for greenhouse gas detection. They have capabilities, but your mileage may vary. The sensitivities vary rather dramatically. Not all of these sensors provide data that have traceable or quantified uncertainty estimates, and not all of this data is freely and openly available. The same thing holds true with the International CH4 constellation, and I should point out that in both cases, they're called area mappers or point source imagers to kind of differentiate the two very large-scale categories. Here's a timeline showing the program of record, and the two US federal agency assets are highlighted here, OCO2, which has been going for 10 years now, and OCO3 on the International Space Station, neither of which has a continuity component associated with it. And note that there is no global mapper, global CH4 mapper capability in this for the US. Here are the point source mappers. Again, this is EMIT. EMIT has very recently been extended to the end of life of the International Space Station, which is ideally 2029. And that should be confirmed next month when they go into their formal end of primary mission and extended mission review. So where does, finally, we got news last week, very exciting news that Carbon Investigation, or Carbon I, has been selected for a Earth System Explorer Phase A study. However, I would like to note that this is still in competition. It's one of 4 missions to be down selected and is not yet an approved flight project. It's just a Phase A study at this point. All right, so where does that leave us for the program of record? We've got several assets that have helped revolutionize space-based greenhouse gas detection and driven US leadership, but there are a number of caveats with the program of record, particularly with respect to continuity. OCO2 is 10 years old, and we are, knock on wood, hoping that it lasts another 10 years, but that is really ambitious for a mission that had a 2-year design lifetime. OCO3 and EMIT are lifetime limited by the decommissioning of the ISS, and planned US launches from this point forward are exclusively NGOs, foundations, and the private sector, with no dedicated GHG mission from the federal sector planned at this time. All right, so how do we then approach this challenge, this grand challenge, as the National Academy of Engineering calls it, of GHG emissions reductions? You all are familiar with the documents that have come out in the recent past from the administration. I just want to highlight 3 things. Number one is, by virtue of these policy objectives that are in 2030, 2050, and 2050 and beyond, in the case of the PCAST recommendation, we're inherently dealing with a multi-decadal problem, and that is the paradigm shift I was speaking about earlier. Here's language directly taken from the PCAST recommendation. The highlights are mine, talking about a multi-decadal strategy for a multi-tiered system that combines what we've called total column and point source measurements. And it's designed not only to deliver information, but maintain US leadership. And all of this is important, again, for 2050 and beyond. Paradigm shift, full stop. We are no longer being driven by discovery-led science missions as one-offs. This is something that is systematic and needs to have our full attention for a full end-to-end consideration of what's needed. With that in mind, looking a little bit more at the timelines, it really breaks down into three natural phases. The first that I've called bending the curve here is the decade from now until the mid-2030s, where we have to demonstrate that we can go from the baseline or historic 1% per year reduction in emissions to something that looks more like 3 or 4% per year, so that we can hit the net zero objective by approximately 2050. And then in 2050 and beyond, we've got the negative emissions era and what is entailed there. All right, so what are the quick requirements that one might think about for a system in the phase one, the 2025 to 2035 era? Well, really, it's identify and mitigate the super and ultra emitters, and it's continue the essential climate variable observations for CO2 and CH4. And the key question that we might ask is, what emission trajectory are we on? And what is the total carbon remaining emissions before we hit a predefined climate endpoint? In the second phase here, we really need to not only continue the measurements of the emissions, but now we need to quantify the natural feedbacks, because in this emissions reducing or declining emissions scenario, there's a lot of information that suggests that the natural feedbacks will not behave as they do currently, and the natural feedbacks at some point will become the largest uncertainty in the annual budgets for both methane and carbon dioxide. And the key question here is, when will we hit this net zero emissions? Finally, in phase three, the 2050 and beyond period, we need to look at what will carbon capture and storage, carbon dioxide removal, and marine carbon dioxide removal systems look like, and are they behaving as expected, or do they in fact have fugitive emissions? Continue monitoring some of the longer term natural systems like the permafrost carbon feedback or oceans for potential rapid carbon emissions that would again offset our budgeting and management. And we need increased sensitivity for non-CO2 greenhouse gas emissions, because if you look at forecasts from the IEA or others, these are anticipated to last at non-zero values for much, much longer than the carbon dioxide net emissions. And then, a milestone question we might ask here is, when might the atmospheric CO2 levels return to their pre-industrial state? All right, so Vanguard, why did I pick that? Well, that was an easy name. It's a shout out to some of the original satellites. And again, it emphasizes that we want to be on the cutting edge and be in the leadership role in developing this kind of technology. In phase one might anticipate delivering something that looks like a double constellation, where you have 3 of these imaging spectrometers with fairly fine spatial resolution, but you can have, with current photodetector technology, up to a 900-kilometer swath at spectral resolutions that are sufficient for CO2 and CH4 detection, as well as some other ancillary information that would help. And with 3 of these, like the new Landsat paradigm, you not only have daily global revisit, but you'll have the ability for more resilience, more rapid revisit, technology infusion, and a gradual and phased replenishment strategy. Similarly, by breaking this apart and looking at land and ocean separately, we could have 2 OCO-like sensors operating in glint mode, which is tailored to highest sensitivity for the ocean. And this would give you synoptic global ocean revisit with the 2 satellites there, so roughly weekly. And I've just said that. So, all right, in phase 2, you would want to augment phase 1 with some more exotic vantages like geostationary orbit, as in what GeoXO is going to do. And so you might imagine putting greenhouse gas sensors on GeoXO. And there are middle Earth or highly elliptical orbits that provide effective geostationary-like observation frequency over the poles. And so one could do that for the Arctic in the northern hemisphere and for the Southern Ocean in the southern hemisphere. And then technology infusion in phase 3, where that kind of initial framework or backbone gets updated not only with replacement sensors, but you now have the ability to have higher sensitivity, perhaps even active sensors for greenhouse gas detection, and it updates to look at the challenges from carbon capture and storage or from some of these feedbacks that we expect to have a slightly longer time horizon. You can augment this with suborbital measurements. Here by Colm, this is a shout out to you and some of the things we've talked about in the past, by instrumenting commercial flights on some of these regional airlines to cover the Arctic. This gets around the cloud problem. This gets around the photoperiod problem. So it doesn't matter whether it's polar night or midnight sun. These kind of flights are going daily to weekly, and you could take advantage of that to just carpet bomb this problem with vertical profiles from instrumented aircraft. In principle, you can do the same thing in the wet tropics, where clouds are also a major problem. However, it doesn't work in the Southern Ocean because there are just so few commercial flights. And so we've got to look other places. Additionally, we can take advantage of something that Ted Scher has been promoting, which is to have the AWARE or Arctic Carbon Warning Network, which I've suggested here could be augmented by systematic carbon-14 observations, because carbon-14 is that unequivocal fingerprint or signature of old carbon or permafrost carbon destabilization and mobilization into active carbon cycling. And we really want to know about that as it's happening, not once it's already happened, so that we can manage this better. Right. And there are just some of the characteristics. And then in the Southern Ocean, talked to some oceanographers, and they suggested updating the Argo floats rather than being on their 10-day cycle. If you could get daily Argo reporting, so when it pops up to the surface and transmits its data, rather than just having thousands of Argo floats, a higher frequency of reporting, particularly from the Southern Ocean, would handle the data problems that we have there. All right, so that's kind of the wrap up of the technical part of things. And I just wanted to remind us all that we operate in a world where there are significant impediments to realizing this kind of greenhouse gas monitoring system. And there are those who would, in fact, have us perhaps, if not keep the status quo, track, as we have been, the highest emissions scenarios well into the future. But there's a lot of reason for optimism. And if you look through not only the literature, but even the public newspaper articles, et cetera, there's a lot of reason to have optimism about this. And so I like this Apollo program quotation from John Kennedy at the outset of Apollo. We choose to do this because it's hard, not because it's easy. And I think that that speaks directly to the new Earth shot that we have as our challenge here in the 21st century. And so there are the summary elements again, and glad to take any questions either now or at the end after Arlyn's had a chance to talk.
Chip, thank you so much for your talk and for your plug.
No worries.
I want to introduce Arlyn, who is going to give us her talk is towards an integrated greenhouse gas observing system. And Arlyn Andrews is part of our carbon cycle greenhouse gas group or division at the Global Monitoring Lab in Boulder, Colorado. So Arlyn, why don't you take it away?
Colm, are you able to hear me and see my slides?
I am.
Great. So thank you guys for the opportunity to present. My talk will be quite complimentary to what Chip presented, and I'm glad he presented a lot of the context for these kinds of observations. My talk, hopefully I understood Colum's charge correctly. It's pretty limited in scope, really primarily to the role of in situ reference measurements to anchor an atmospheric greenhouse gas observing system. So I won't be talking about NOAA's ocean measurement program or about efforts that are really aimed at tracking emissions or fluxes directly. So I won't be talking about eddy covariance measurements, which is something that the DOE has invested heavily in. So with those caveats, this title slide shows a montage of different platforms and methods that are used to measure atmospheric greenhouse gases, and including satellite observations, but importantly, also showing a lot of the in situ measurement strategies, which complement, anchor, and add value to satellite observations. So just to kind of step backward and say, well, what processes are we actually aiming to detect, quantify, understand, and track? Ecosystem photosynthesis and respiration, and sort of other large area fluxes are things that we cannot track very well directly with inventory-based methods. And so the atmospheric data provides a really unique perspective and information about ecosystem greenhouse gas emissions and removals. We're also looking to track carbon climate feedbacks, such as the release of CO2 and methane from melting permafrost, from CO2 fertilization, from ecosystem changes, such as evolving wetlands, increased fires, stressed out tropical forests, and things like Arctic greening, which is the encroachment of ecosystems to higher latitudes as the climate warms. Also anthropogenic emissions, and that's at the city scale, landfills, agriculture, industry, oil and gas production and distribution, et cetera. And as Chip mentioned, the efficacy of mitigation efforts. So can we see signatures of emissions reduction and programs such as, or efforts such as carbon dioxide removal in the atmospheric abundance of major greenhouse gases? So, you know, the tool that we use to translate atmospheric observations into information about emissions and removals are these data assimilation systems. And these are 3 examples of assimilation systems that are supported by US government agencies. So NASA JPL has the CMS Flux system. NASA GMAO has the GEOS CF composition forecast and composition tracking capabilities. And we at NOAA have a suite of modeling tools that fall under the label of Carbon Tracker. And most of what I will talk about here is really applicable to larger scale. So I'm not going to talk too much or really at all about point source monitoring, but more about regional to continental to global scale tracking of these processes.
Arlyn, just a quick question. This is Diane. Can you please hit the hide link where it says stop sharing at the bottom so we can see your full slide?
My computer just kind of hung up on me here. Hide. And then let me see if I can get back to the PowerPoint.
Great. Thank you.
Sorry, I think it just kind of got overwhelmed by that movie. Okay, so are you seeing the slideshow view or the presenter view?
Presenter view.
Okay, I think I have to click this button over here. And then it takes a second for it to center itself. Okay, so something that Chip didn't talk about is the US greenhouse gas center activities. And that is one aspect of implementing the national strategy, which is the document that's kind of screenshotted there in the lower right. And Chris and Chip did talk about the national strategy. The Greenhouse Gas Center is an effort to coordinate across the agencies. And one element of that is the data portal that we're seeing here. And I know I saw that RG and Shanna from the US Greenhouse Gas Center were online. So this portal is, the initial releases of it, we're on release 2 now, are really trying to gather and present data from across the agencies. And we are continually working to add to the content. And NASA and NOAA, NIST, and EPA are the agencies that are leading this effort. At the global level, the WMO has announced and been working on implementations for plans. In fact, have just released a new implementation plan for the Global Greenhouse Gas Watch Program. And that is aiming to coordinate greenhouse gas observing and data assimilation activities at the international level. And I also want to mention GCOS, the Global Climate Observing System, which predates the Global Greenhouse Gas Watch and has done a lot of work to try to coordinate and describe what a climate observing system looks like, including greenhouse gases. And something that I really felt like it was useful to bring awareness to is the GCOS monitoring principles. And I've highlighted a few here in blue, and I'm not going to read them or even the ones that I've highlighted, except I will say that number 7, a high priority for additional observations should be focused on data poor regions, poorly observed parameters, regions sensitive to change, and key measurements with inadequate temporal resolution. And that the conversion of research observing systems to long-term operations in a carefully planned manner should be promoted. And that's really where we are at the national level and at the international level. And they also have monitoring principles for satellite systems. And the 2 that I highlighted here call out the need for complementary in situ observations, and the need, I'm sorry, I don't know why this keeps advancing, and the need to identify random errors and time-dependent biases. And I added an editorial comment in pink there, that it's not enough to just identify time-dependent biases, but we actually need to have coverage and density of reference observations that are sufficient to correct systematic biases that are significant in the sense that they're large enough to complicate or confound or actually give incorrect information about the underlying processes that we're trying to study. So in this case, greenhouse gas emissions and removals. So NOAA's network consists of flask air sampling and in situ measurement sampling systems. We provide extremely precise measurements of CO2, methane, nitrous oxide, as well as many other greenhouse gases and process tracers. We serve as the WMO central calibration laboratory for CO2, methane, N2O, and other gases. And that actually allows us to, we provide this standards and calibration scale information that is used worldwide by partners in the WMO Global Atmosphere Watch and soon the Global Greenhouse Gas Watch activities, so that we can have consistent measurements worldwide and really be able to confidently interpret differences across space and time. And some of the findings from the Global Greenhouse Gas Reference Network are over time, and some of this, going back to 1800, obviously takes into account ice cores and other things, but CO2 is responsible for 66% of the climate forcing by all greenhouse gases. And CO2 is extra nasty because the emissions accumulate in the atmosphere over very long time scales. And 40% of the Ford Model T emissions from 1911 are still in the air today. So the CO2 that we continue to emit, we're committing to having it in the atmosphere for a very long time. And in terms of methane, something that's quite unique from our measurements that you can't infer from satellite data is that as we've seen methane increase rapidly starting around 2007, we've seen the isotopic, the composition of the 13C of methane isotope drop. And that's not consistent with that increase in methane emissions being driven by fossil fuel emissions. Instead, it indicates that these increases are primarily driven by biogenic sources, such as from wetlands or ruminant agriculture. And that's not exactly good news, because if it were being driven by fossil fuel methane, then we would know what we needed to do to make that increase just stop or turn around. Whereas if it's some kind of a carbon climate feedback, that's actually much, it's much harder to deal with via emissions reduction policy. Also at the global scale, the role of ecosystems and oceans is such that about half of fossil fuel emissions to date have been absorbed by ocean and land ecosystems. And that's not inconsistent with what I said previously. So the emissions that occur in a given year, about half are taken up by oceans and land ecosystems, and that's approximately equal. So a quarter taken up by the oceans and a quarter by land ecosystems. But of the remaining, the half that remains in the atmosphere, that stays in the atmosphere for a very long time. And interestingly, so far over the period that we have measurements, we can show that the ocean and ecosystem carbon sinks have been keeping pace with rising fossil fuel emissions, so that half that of fossil fuel emissions has been relatively constant over time, even though emissions have increased. But you can see from the figure on the left, which I don't have time to explain very much, that there are large year-to-year variations, and these are driven primarily by terrestrial ecosystems. But the processes that cause these year-to-year variations are not particular, they're poorly understood in that models don't reproduce them. And so how can carbon dioxide removal and other mitigation efforts succeed when we lack fundamental understanding of the natural carbon sinks? And natural is in quotes because natural ecosystems doesn't really, all of the ecosystems that exist in the modern world are significantly perturbed. So we measure more than about 50 species, including a whole bunch of tracers that can tell us about processes, as well as a comprehensive suite of greenhouse gases, including some of the ozone depleting substances and their replacements that are greenhouse gases, and stable isotopes and radiocarbon, which of CO2, which Chip already mentioned is a unique tracer of ancient carbon. So he mentioned it's used to track permafrost release in the Arctic, but it also can be used to separate biogenic and fossil fuel CO2 emissions. This slide just shows how having a suite of tracers can tell you something about the sources. So it's really aimed at quantitative source attribution for carbon gases. So things like HFC 134A is a refrigerant that has for a long time been in automobile air conditioners. And so when you see that multiple species have enhancements in the boundary layer, it can help you parse out the sources and sinks that are contributing to the atmospheric burden. Radiocarbon, again, I'm not going to go through this, but radiocarbon is not present in fossil fuels. Its half-life is only 6,000 years, and so it's entirely absent from fossil fuel carbon. And so it's a uniquely valuable tracer for fossil fuel CO2 as distinct from total CO2, which contains signatures of biogenic fluxes. We have been investing in a new surface to stratosphere super site capability. And currently we have this at one site, which is in Colorado, where we have a tall tower. We have repeat air core balloon profiles that go to the stratosphere, and we have aircraft profiles. And so this allows us to get more confident comparisons of in situ measurements to the satellite data. And ultimately, we will have an EM27 sun solar spectrometer deployed there as well. And the figure on the right is an example of some of the high definition vertical structures that show up in profiles. And so that horizontal line at the top at near 17 kilometers is coincident with the tropopause. So you can see CO2 and methane falling off above there. You can see a plume between 8 and 10 kilometers, and you can see enhancements in CO2 in the boundary layer. And so the high definition vertical information that we get from in situ measurements provide strong constraints on emissions as well as on simulated atmospheric transport. And we need to do simulated atmospheric transport with high fidelity if we want to accurately infer emissions from atmospheric data. So NOAA has invested quite a lot in expanding their aircraft in situ greenhouse gas measurement capabilities, and much of this, all of this work really has been led by Colm Sweeney with contributions from other people in the group. And because of their work, we now have the ability to deploy fully autonomous in situ measurement systems. And so we are really trying to get vertical profile information from the tropics in Africa and Brazil, and also from repeat Alaska Coast Guard flights. And we're transitioning from sort of dedicated flights where we pay them to go and fly a profile just carrying our instrument to more of a ride-along mode. So like in the case of the Alaska Coast Guard, they do a lot of recon flights and training flights. And if we can have our measurement system turned on for all of those flights, we'll collect a lot more data. We're also doing repeated intensive campaigns to visit areas that are not captured by our network and to assess the density of sampling that we need and what we're missing with just our routine profiles, as well as ongoing work to track oil and gas emissions from aircraft. Here's another example just showing some of the structure that we see up on the upper left. Those are profiles from Brazil. And in the lower right, that's from Alaska. These data sets were collected in partnership with NASA, with additional support provided by NASA, in particular from the OCO2 3 project. And in the example from Uganda, we can see that the assimilation of satellite retrievals into the data assimilation system improves the agreement with these aircraft observations that are independent. We also can see that the current generation of models doesn't capture the vertical structure. So it's not taking full advantage of all of the information that we can provide with in situ aircraft observations. So internationally, I just want to put our measurements in context. There are lots of countries around the world that are contributing to greenhouse gas in situ measurements that will hopefully ultimately be part of an international reference network. But not all these sites have stable long-term funding. There are coverage gaps over Siberia and the tropics. We don't have very much vertical profile data available. It's primarily available over North America and the global sites I just mentioned, and that we have opportunities for expanded measurements via commercial aircraft and ships. And so I did want, there are ship data that are not shown on here that NOAA is collecting, and Column's involved with that as well as NIS from Japan. And in terms of commercial aircraft, the Japanese, again, NIS has a program called Contrail where they've instrumented a handful of long-haul aircraft with greenhouse gas sensors. They so far have only been measuring CO2. IAGOS is a European program, and they measure CO2, methane, and CO. NOAA, again, Column's team, has demonstrated a fully autonomous measurement system on the Boeing Eco Demonstrator. And just as an example of showing the potential of commercial aircraft measurements, the National Weather Service has a water vapor commercial aircraft sampling program, and they have instruments on 137 aircraft, and they collect more than 1,000 profiles per day. So having that kind of high resolution vertical information that I showed on the earlier slides at the level of 1,000 profiles per day would really change the game in terms of being able to keep track of surface emissions and processes. And I don't have a summary slide, so that is all I have.
Arlyn, thank you so much for your presentation.